Hello everyone, this is Doug, and in this video we're going to talk about some of the major polysaccharides, just three of them, specifically amylose, cellulose, and glycogen. So if we take a look first, right, just remind ourselves what a polysaccharide is. So poly meaning many, and then like I said before, saccharide meaning like a sugar, so many sugars, many sweet things. The first polysaccharide I want to look at is amylose, right? This is the one that's found in plants. This is what we commonly call starch, so think of something like, like rice, or potatoes, something like, corn, just grains in general, wheat, stuff like that. So this is your starchy stuff. Now I have two drawings down here of amylose, and if you take a look at this, right, it looks like we have a whole bunch of repeating subunits, right? These are all combined by condensation. And each and every one of these subunits here is a glucose molecule, right? This is one glucose, two glucoses, three glucoses drawn out. And then in the square brackets with the 300 to 600 written there, that means just repeat that 300 to 600 times. And so for amylose, what we see that amylose is a polysaccharide made out of hundreds to thousands of glucose molecules, hundreds of thousands of glucose molecules. So its subunit, its monomer, is glucose, and we'll summarize this in the last slide. But it's made out of a whole bunch of glucose molecules, and you should be able to recognize glucose by the drawing, right? At carbon 2 we're down, carbon 3 we're up, carbon 4 we're down. But what I also want to know here, right, is what type of linkage are connecting these glucose molecules, because that's going to be really important for us deciding which type of polysaccharide are we talking about here. So I've got my carbons 1, 2, 3, 4, 5, and 6. And 1, 2, 3, 4, 5, 6. And you'll see the same thing for this one over here. I'll put the numbers just so we can confirm and convince ourselves. But if I take a look at this one, right, it looks like I'm connecting carbons 1 and 4, so I know it's a 1,4 glycosidic linkage. And at carbon number 1, right, it looks like my OH is more going down than going up. So remember that if it's going down, that's alpha. So these are specifically held together by alpha 1,4 linkages. And so all of these, amylose solely has alpha 1,4 linkages. It's just a whole bunch of glucose molecules put together. Again, hundreds to thousands. Now I wanted to show you this drawing down here because this is supposed to mean the same sort of thing. This is another drawing. This one down here is the same thing, but I think it looks a little bit funny only because I've been teaching you guys, right, that if you look at things like this right here, that a bend in a drawing means that there's a carbon there, and that's not what this drawing is trying to imply. This drawing is supposed to be the same thing. These are supposed to be the same exact molecule showing the same linkages as the one above it. They're drawing this down and to the right just to make it more angular. You will see more with beta in a second that it makes a little bit more sense, I guess. But they want to be able to write it out from left to right in like a textbook or something like that. And so this is supposed to mean, if you look at this, it's supposed to imply that at carbon number 1 here, right, we are moving in a downward direction. This is supposed to be explicitly downward direction, showing you again that this is an alpha linkage is the idea. And so this is not a carbon. This bend is not a carbon. This is not some new molecule with a new carbon right there or at that spot over here. Those are not carbons. It's just another way to draw these linkages. I prefer the way up here, so for my materials, you'll see me draw it more like this up here, where I have them sort of at an angle and sort of like that V shape, just to indicate kind of, right, that they're both moving down in an alpha position, and there's clearly no carbon there. So again, amylose is a whole bunch of glucose molecules that have alpha 1,4 linkages. And that's different than our next molecule, which is cellulose. Cellulose, you'll see, well, first of all, cellulose is what's found in animals, right? It's that makes, or sorry, not animals. Come on. It's not in animals, it's in plants. It's in cell walls, right? They're a structural feature for plants, not in animals. Animals do not have cellulose. We do not have cell walls. Sorry about that. Yeah, they're just found in plants, and this is one of the things that we might call fiber in our diets, right? When you find fiber on your nutritional list, that's one of the components that we're talking about. Fibers are just indigestible things that you eat. So cellulose would be one of those. And again, if you look at cellulose, right, if you look at all of these monosaccharides here that are making up this polysaccharide, again, this is just a whole bunch of glucose molecules. So this is, again, hundreds to thousands of glucose molecules put together. So once again, glucose is that subunit, glucose is that monomer that's being repeated over and over and over again in this polymer that would be cellulose. But now if you look at cellulose, right, we want to ask ourselves, well, what type of linkage is this? Why is this kind of making a like an upward stair-step pattern here? So I've got carbons 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. I'll just do one more here. 3, 4, 5, 6. And if you take a look at this one, it looks like we're still connecting carbons 4 and 1. So I still got carbon 4 connected to carbon 1. But only now at carbon number 1, it looks like the OH is going up, not down. All right, so we are talking about the beta anomer, not the alpha anomer. And so in cellulose, we have all beta 1,4 linkages, 1,4 glycosidic linkages. And again, that's because it looks like we're connecting carbons 1 through 4 in all of these links. And in all of them, we're moving up at carbon number 1, not down on carbon 1, right? When we were moving down, that was an alpha 1,4. That was what made something amylose. Here, for beta 1,4, then we're moving up. That is cellulose. Different polysaccharides, different functions, different relationships to us in our diet. And then again, like in the last one I showed you, you might see molecules drawn like this, where they have this sort of funny-looking linkage again. And again, the idea here is that that is just trying to show that at carbon number 1, that you're moving in an upward direction at carbon number 1. But again, that bend right there is not a carbon. So it's the same sort of biochemically drawing. So that's not a carbon, that's not a carbon, right? All of those bends right there are not carbons. So in organic chemistry, we said every end and every bend is a carbon. Here, still not a carbon. So don't freak out, don't get confused by it. It's just trying to show a beta linkage, trying to show that it's moving up at carbon number 1. That's the big idea. So cellulose and amylose are really different only in that they have, one has alpha linkages, one has beta linkages. I'll talk more about this in the last slide, but the reason why this is a dietary fiber, right, which again means that we can't digest it. So let me write this here. So fiber means undigestible. Is because it has beta linkages. And we don't have the enzymes to break up these types of beta linkages. So we lack those enzymes. And by we, I mean animals, basically. Like no animal makes cellulase. However, while animals lack those enzymes, microbes do not. So microbes do have cellulase, which can break up, breaks up those beta linkages. So when you hear about like animals like cows or goats or something like that can eat grasses, which are just largely, which have a lot of cellulose, and they are managed to somehow get nutrition out of them, it's because their guts are loaded up with these microbes that actually can break up the cellulose into glucose molecules, and then they kind of swallow that whole thing, and they're able to actually get the glucose out of it that way. While the cow or a goat cannot break it down, they have microbes in them that can break it down. And it turns out we do too. It's kind of dishonest for a nutritional label to say that the grams of fiber don't count, or anything from cellulose doesn't count in your nutritional thing. We actually do break down. Last I saw, the number was about 25%-ish, 20 to 25% of that fiber does get broken down in us, in our guts. And it kind of depends person to person, of course, what your microbiome is like. But we actually do break down a little bit of this, and we do get some of the calories out of it. So you might hear completely undigestible, but really it should be kind of mostly undigestible. It's not really completely undigestible. We can break this down a tiny bit. And by we, I mean the microbes in us, not us. We do not express the gene to break up the beta linkages. And then our last polysaccharide here is glycogen, right? So glycogen is found in animals. I got that right this time. And this is kind of how we store carbs, right? So amylose, starchy things, and amylopectin, that's how plants store their carbohydrates. And then we store carbohydrates with glycogen, right? So we being animals again. We don't store a lot compared to fats, but we do store some carbohydrates so that we have sort of a quick way to replenish our blood sugar. If you have to run away from bear real fast, you're able to release a whole bunch of glucose into your bloodstream, so you can still function and do glycolysis and everything like that. So again, yeah, we store that in your liver and muscle tissues primarily. And so if you look at glycogen, I gave you just a little piece over here on the left, where again, if we look at what these subunits are, this is again glucose. So again, we're talking about hundreds of thousands of glucose molecules. And I drew a little piece here, and on the right is kind of one larger piece of glycogen with a protein that's holding it together. And you'll see that it's just highly branched. There's all these little branches here, and so you get your glucose branches like crazy, which is a feature only or primarily found in glycogen, amylopectin, but we're not talking about that right now. So it has lots of branching, which allows us to break up that macromolecule much more quickly because our enzymes have to attack end pieces. And so if we need to get at these, we're able to have enzymes attack these little pieces and start chomping it down and releasing glucose way faster than, for example, amylose, which only has one end piece because it's all linear. And this branching comes from the types of linkages that we see, right? So let me draw some numbers on here for us. So 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. We should see a familiar linkage here, right? So again, if you look at this spot, looks like we have our nice alpha 1, 4 again. So here's your alpha 1, 4, just like amylose had. So alpha 1, 4, right? Because at carbon number 1 here, we're moving in a downward direction. So that's alpha 1, 4. But we do have this new linkage up here. So if you look up here, right, where the branches, where all those branches that I was talking about on the molecule on the right, here at carbon number 1, it's definitely moving in a downward direction, so that's still alpha. But I'm not connecting 1 and 4, I'm connecting 1 and 6. So this would be an alpha 1, 6. And so what we see that kind of makes glycogen unique among these three is it has not only alpha 1, 4s like amylose, but it also has alpha 1, 6 linkages. So it has both, which is what gives us that branching structure. Cellulose and amylose don't have branching structures, just glycogen of the three that we're looking at. So if I was to kind of summarize these, right, so these are the three important polysaccharides that I want you to know. There are lots more out there. There are the chitin, there's amylopectin, there's other ones out there, but these are three big ones for us that we want to compare and contrast. For amylose, right, we said that the monosaccharide was glucose. It's just a whole bunch of glucose molecules repeated over and over again. It only had alpha 1, 4 linkages, and this was from plants, right? These were our starches. So think of a starchy food. You'll find that this is a major component of starches. Was it digestible? Yes, it is digestible, right, because it has alpha linkages. We can break up alpha 1, 4s, no problem. We make alpha 1, 4s in glycogen. Now, if I compare that to our cellulose, right, cellulose also had glucose as its monomer, only it didn't have alpha 1, 4s, it had beta 1, 4s, right? So at the one spot, it went up, not down. Where do we find this? It's also in plants specifically, right? We would refer to this as like fibers or, dietary fiber. Was it digestible? No. And again, that was because it has beta linkages, which we don't express enzymes for. The microbes in our guts can, but we do not express that gene. So it's kind of hard for us to break down, which is why we consider it fiber and generally non-nutritive, even though it is a little. And then lastly, glycogen here, right, also is made up of glucose, right? So these are all made up of glucose. These are all polymers made out of glucose. And then glycogen has alpha 1, 4s and alpha 1, 6s. So it has both of those types, which is why it branches. And again, we find this in animals, specifically in their livers and muscle tissue and muscles. And that's what we break down relatively quickly. Your glycogen levels go up a bunch after you eat a carby meal. They go down when you go to sleep because you use a lot of that. They go way down if you go on a run or something like that. And is it digestible? Yeah, technically it is digestible. You probably don't eat a lot of glycogen, but certainly we break down our own glycogen. If for some reason, and I apologize if anyone's vegan or something like that, but if for some reason you did kill an animal and you ate it right away, it probably would still have some glycogen in its muscle tissue, and you'd have no problems eating that. No problems at all. So those are the three big polysaccharides I want you guys to know. If you have any questions or comments, please go ahead and leave them down below, or you can email me. And happy studying. Review these things and do some worksheets. Take care. Bye.